O is called the shear center. The shear center is such that as long as transverse loading is applied to pass the shear center, they wouldn't have induced twisting on the cross section. So those are our calculations for those things. This is the distributions of the shear stresses, and in particular, the maximum shear stress we identify occurred at this section here, right across the neutral axis. Okay, so that is the one we did last Friday, and today we continue on this example. We talk about a little bit more. On the same cross section, assuming we have transverse loading that is passing through the centroid. Okay, so for this case, right away we know that because the transverse loading doesn't pass the shear center. So under this case, this cross section will under two kinds of the shearing. One is the shearing induced by V, and the other one is the shear stress due to induced twisting. Okay. So that means the total distribution of the shear stress for this question will come from two portions. One is the one is from tau equal to VQ over IT. The other one is from the twisting, that is our torsion things. So again, for this example, we can decompose this one into two scenarios. The first one is we deal with the cases without twisting. So that means assuming V applied through the shear center. But this one, in able to make equivalent with this one, we must have induced twisting. So that means this one we can decompose into two scenarios. And this is due to superpositions. And this one is what we did last week. And then we will be able to calculate the shear stresses at any single point on the cross section. In particular, in the maximum case, the maximum shearing for this case is here. Okay. For this one, this is the induced twisting. Okay, and again, if you remember our first pictures, once we have the transverse loading, then I show you this kind of cross section twisted in this way, and that is due to this one. For this case, that is come to our exam, the test one, the contents of the test one, and if you remember, is this. Let me try to recall. If you remember our membrane analogy, so if we have this kind of the thin structures, and then from the membrane analogy, we know that the contour lines is something like this, right? And then we know that the gradient of the contour line is proportional to the magnitude of the shearing. So in that exercise, we know that the maximum shear stress is on the two sides here. Okay. So the same thing, if we have the twisting like this, then the directions of the shearing in the twisting should be follow up these notations, this kind of circulation like this one. Apply this concept to here. So here we simply bend this geometry into kind of this shape. Okay. So that means now the twisting is like this. So basically the shear flow or the shear stresses around the parameter must be in the same circulations of this. Okay? Okay. And now for this case, then we can calculate we'll be able to use the old formula to calculate what will be the shear stress corresponding to this kind of scenario. So for this case is this, if we would have the transverse loading applied to any point which is not a shear center, then we want to know what is for example, the maximum, the shear stress. Okay, so the maximum shear stress would be contributed from this one and this one. Okay, for this one is from our previous calculation, this number here, 3.06. Okay, this one is obtained at here. Okay, so you can ask me how do I calculate that one. So this number simply is this. We're looking at this geometry. This is the neutral axis. You simply take up this as a shaded area for your Q. So tau maximum for this case will be equal to VQ over IP. The T will be the thickness here. Okay, so this number basically is calculated using this geometry. And then now we fix this one, then we simply work out this one. This one is an old stuff. And that one we're simply using this formula. So hopefully you still remember, then probably dig out the old formula and the shear stress due to twisting. You remember we have this formula, right? And we haven't exercised for a couple of weeks. Even for myself, I need to dig out the old note. Okay, but anyhow, it's doable. Okay, it's doable. So we simply plug in, and what is T? T is the value of this one. And what is T? T basically is equal to how much? T basically is equal to V times this distance. Right? So you need to calculate T first. T basically is the value of OC multiplied with V. That is the one here. And C1 is the parameter we can check out from the table. We have a table there. And with the information of the things. And the A and B are the dimensions parameters per our notation in the formula earlier. So to calculate this one should be fine, and then we got this one. So the total shear stress and maximum, this one is constant, okay? And then the maximum we simply plug into the previous one we calculate from the two portions. That is everything here. So for this example in particular, the twisting induced much more than visual IT. Yes.
So if you gave us a problem like this, would you give us A, or would we have to solve for it?
A?
Yeah, like you.
For this one, I think
hard.
A is you simply calculate that one simply. I think this domain, you simply calculate the whole dimension, the parameters here. This is 4, 6, and 4.
Okay.
Yeah, or sometimes if you want to calculate from the middle line to middle line, I think that's okay. Again, this one.
But would you like? Because I remember last week you were like, oh well, you can be more accurate,
yeah,
but
more
it really
accurate.
doesn't
yeah,
matter
that one
to
really
you.
doesn't matter to me. It's
would
not
it
critical.
matter in this sense here too? Like, would you expect us just to take the outside, or to take like from middle to middle?
I would expect. Why not we just take follow up this one? We take them from the outside here.
Okay.
Okay. So this is the pretty much all the representation of the examples for these chapters, and follow up is a few examples here. This one is the similar example. Do I have? Okay. So this one, we look at this is on your handouts, and if you have the handouts with you, you can check it out. I don't have any more. No, I don't have any more. So, oh my God.
Of course I did. Thank you. You did not really once.
That was just one. Okay, that was also good for you.
So for this one.